So, last speaker for today is Øystein Sorensen. I hope I pronounced your name correctly.
Yeah.
And he is associate professor in statistics at the University of Oslo. And given his name, I assume he actually is Norwegian. So that at least makes one proper Norwegian speaker here at this Oslo user meeting. So that's very nice. Øystein has a number of research interests, and he does applied data analysis, but he also does more methodological work. And there's a particular emphasis also on software development. This has led to a number of R packages. One of them is the Metagam package, which he will now tell us more about. So please take it away.
Thanks. You know, it's incredible that we can sit here, people from all over the globe, and talk about these things. So what I'm going to present today is, as you said, about the package called Metagam, which is about meta-analysis of generalized additive models and other nonlinear models. So, sorry, there we go. Yeah. So this, I'm just going to say a few words. So the package was, it's not very deep statistics, but it's based on something that we needed to do. We need to solve a problem, and we figured out that there was no R package, or maybe even no published paper for how to do this. There were some papers in completely different fields, but I'm going to tell you more about this now. So in, for example, brain imaging or genetics, where you have a large number of variables, you also need very large sample sizes. And in order to sort of achieve the necessary sample size to get necessary statistical power, it's often necessary to combine data from multiple studies. For example, and in addition to increasing the statistical power, you also get higher statistical or predictive accuracy for building prediction models. However, sharing data, especially if it's data on humans, can be quite challenging because, you know, privacy. Like I work on images of people's brains, maybe combined with detailed information about their genes. Then even though we have collaborators, it's not that simple to share those data, very sensitive data about people. It might be more like legal stuff. For example, that at the time of data collection, you didn't ask the participant whether they approved that you could share your data. And there could be things like different data formats. Different variables mean different things in different countries, for example. So in meta-analysis, you kind of circumvent this problem. And I'm going to just show like it's very simple meta-analysis of a linear regression model. So if you have G groups, like with group, I mean research groups, and each group has a data set. Then you can let each group fit one model, like a statistical, this is just a simple linear regression model to the data. And then they can share the parameters, the beta hat, the slope, what's the effect of this X. Then they can share these parameters, and you can get the meta-analysis, or you know, you can combine the data to get higher statistical power. So that's perfectly fine. However, yeah, and you find the joint estimates, as you say here. So the meta-analytic estimates is a weighted sum of the individual estimates that you get from each of the groups or each of the sort of sites that collect data. However, meta-analytic methods typically require parameters or numbers that mean something, and they have to be identical or similar meaning across studies. So today we've heard about effect sizes, we've heard about so structural equation models where you care about correlations and path slopes along path variables. However, many problems require so-called semiparametric methods, which is that rather than having a regression coefficient beta times x, you have some function f of x because the underlying effects are nonlinear. So let's say you do the same thing. You have G different groups that have their data. You're not allowed to share the data, but you can't use like traditional parametric models. Instead, you have some so-called non-parametric function of the data in each group. How do you combine these? So in this particular problem, we were thinking about generalized additive models, GAMs. And GAMs, so they consist of a weighted sum of basis functions, which we call B here, and they actually have coefficients. So you have an alpha hat, which we call it here. So each group, each site estimates, say, capital K different parameters with their basis functions. However, so if the basis functions were the same across all the sites, then you could just run standard parametric meta-analysis on these alphas and run that and multiply that with the basis functions, and you would get an estimate of the function that uses the power from all the studies. However, sometimes, or often actually, the basis functions have to differ between the different sites or between the people who do the different studies. For example, because the range of these explanatory variables, say if that is age, for example, and you have a young sample in one place and you have an old sample somewhere else, then the locations of these basis functions have to differ. And then these parameters are no longer comparable. So you can't just combine alpha hat 1, like the first spline coefficient from one group, and combine that with the first spline coefficient from another group, because it multiplies something else. So, and the example that motivated this package is a research project, an EU project where we had data from different cohorts across Europe, and we were interested in how sleep quality was associated with the lifespan development of the hippocampus. So the hippocampus is one of the most important parts of the brain. For example, the one that gets it becomes much smaller, for example, when you get dementia. And also dementia is associated with poor sleep. So we were interested in the association between sleep and hippocampus. So we had 6 European partners, but at least at the time that we developed the package, we were not allowed, for regulatory reasons, to share these brain imaging data across countries, which means that we let each group fit the model where you had one function of age, and we have a function of age and sleep. So this F2 is how the effect of sleep, which is the X, interacting with age, how that affects Y, which is the hippocampus volume. So you have a model like this. In reality, it was actually a mixed model with even more correlations of these. So we had random effects here as well, but this sort of makes the point. And from each group, we got an estimate here, for example. This is the estimate of how the hippocampus volume develops across the lifespan. And what we can see here is that, for example, from this study named CanCan, they have data from 20 years up to 90 years. Whereas Whitehall 2, which is the Oxford University, they only have people between 60 and 85-ish. So you have very different ranges, which means that these non-parametric functions, they used very different basis functions, because, for example, Oxford, they couldn't have any knots in this range from 20 to 60 because they have no data there. So then the model would crash and also be very inefficient. And we also see here that even though this is not extremely nonlinear, these effects are nonlinear in the sense that it's very plateauing in the young, sort of from 20 to 40, and then it gets very fast down. So this is how the hippocampus develops, and you have similar effects with sleep. And we were interested in combining these effects across these studies simply by combining the curves with their prediction intervals, or sorry, standard errors of the fits. So what we figured out then was we sort of reinvented something that's been done in epidemiology, actually within air quality, where you have air quality measurements from different cities. And what we did was that each group does not share its data because we're not allowed to do it. And we couldn't share the parameters because they couldn't be meaningfully combined. What we instead said is that each group shares a function which can take some new variable X, like give me some new age, give me some new sleep score, and return the predicted outcome with standard errors. So when we have that, we don't need the data. We can just get one function from each site and then combine these functions with some weights, and these weights are inversely proportional to the prediction standard errors. So it should actually be W as a function of X here, because the uncertainty depends on this x. So if I want to plot a combined function, like combining all these 6 plots from 20 to 90 years, I would set this x here to be a grid from 20 up to 90, and the weights would be the inverse of the prediction standard error at the same point, the inverse of the function standard error, and then you have each function's prediction at that point. So in R, it means that each group does something like this on their own with their own data. They fit the GAM with some nonlinear functions. So they don't need to care that much about which other variables they control for. For example, that doesn't have to be the same across the studies, but they have their own data, which cannot be shared. Then they send us the model fit, mod_G, to the people who are going to do the joint analysis and publish the paper, which uses the power from all these studies. And then they can predict from this model G on some common grid, some common new set of explanatory variables where we want to look at the functional relationships. However, in R, if you ever look into these objects, like for example, the object returned from the GAM function or from GLM, LM, whatever, they contain a lot of individual participant data. So we can't just say to people, okay, fit the model, don't share the data, but just send us the model object. Because that model object contains a lot of data, both like very explicit, but also more hidden data, like transformed values. You can get like QR decompositions of the actual data, which you can then transform back and then reveal the data, which you don't want to have revealed. So that's where the Metagam package comes in. So if you load the Metagam package, you would still fit a model at each place. So, you know, Oxford fits their model, Cambridge fits their, Barcelona fits their model. However, we have this package, now this function in Metagam, which is called strip raw data, which removes all the raw data, like point or element by element from the model object, so that you don't share any raw data when you share the model. So then we have each site does strip raw data on their model, and then they get this object, which I call mod_G safe, which is a safe model to share with the rest of the world. It only contains the things you need to make prediction. It does not contain any information about the data that can be used to identify the people there. Then all of them send these model fits, the safe model fits, to the central hub that does the meta-analysis. And we combine these models into a list. And then we get meta-analytic estimates by calling the Metagam function with this list of models on some common grid of variables. So I'm going to show it here from a paper that we did. So in this case, we actually ended up through a lot of regulatory work to be able to combine to get the data into one place. But the meta-analysis here is the green line, shows the meta-analysis that we got, like the effect size. This is the hippocampus volume, and this is the effect of sleep duration on the hippocampus volume at different ages. So like being below 0 means that sleeping less is associated with a smaller hippocampus and vice versa. And as you see that since the confidence interval here surrounds 0, the effect was definitely not statistically significant, but we get, you know, one overall meta-analytic estimate. And since we were so lucky to actually be able to combine the data in the end, after developing all this infrastructure to do the meta-analysis, we could also compare it with the mega-analysis, where we analyze the data in one place. And as you can see, there are some discrepancies, but they follow the same sort of general pattern. So this Metagam package also has some methods for post-fit analysis. You have the typical summary methods, and you can plot the individual functions together with the overall meta-analytic estimate. We can also look across this grid. Say here we're interested in age, for example. How much does each model or each sample contribute to the overall estimate? So we call it the relative influence plot, where we see that at the lower ages, the green one here is the LCBC, the Oslo sample, they totally dominated. And this is, of course, partly because they have higher sample sizes, but it could also be because they had lower standard errors. But then at the ages around 70, all of the study contributed quite a lot to the overall fit. And we can also plot the heterogeneity as a function of age. So heterogeneity, I'm not really an expert on all these measures used in meta-analysis, but it's a test on whether the effects are different in, I think at least one of the study is significantly different from the others. So you can look at how the heterogeneity varies with the explanatory variable. So what the Metagam package offers, to summarize, is that it lets you fit generalized additive models in a distributed way so that you don't have to combine the data into one place. And that's useful, especially when you're working with human data. I think also, for example, if you're a bank or some other sort of private industry where you have a lot of regulations imposed by the GDPR, this could be a way to utilize data from different parts of the organization without actually analyzing them in one place. So, and the second thing of the Metagam package is that it removes the raw data from the model object. And currently this works for the MGCV and the GAM4 packages, which are the sort of mainly used packages for analyzing generalized additive models, which is really, just going through the model object that's returned from the original fit and removing all those list elements in there, which actually contain the data. And the third point is that it combines these fits meta-analytically. So it's sort of a meta-analysis of prediction models is really what we do. And it gives estimates which are quite close to what would be obtained if you had the complete data available in one place. And it also gives convenience functions for visualization and statistical summaries. So some future directions is that we might want to do this for all the classes of nonlinear models. And we might also use it to do some sort of Bayesian simulations. If you have a posterior distribution from each sample, we kind of have that too, and trying to combine those posterior distributions. And also the algorithm for computing p-values now is very, it's a bit inefficient because it doesn't use the effect sizes. It only uses it combines the p-values, and that's a bit inefficient. So we might come up with some new algorithms for computing p-values. So thanks to my co-developers, Andreas Brandmeier and Mo Athanasia, or Mo as I call her. Yeah, if you're interested in more details, the package has a website, and we have a paper describing these things in much more detail than what I explained now. So that was all I had. Thank you.
Thank you for this presentation. All right, we already have a question in the chat from James. James, you can also just go ahead and ask your question.
Sure. Øystein, this is really cool, and I think it seems like the sort of thing that could be extremely useful beyond even the context of the examples you gave. In education right now, there's a lot of interest in understanding variation in treatment efficacy across participant characteristics, and where the different studies may be conducted on the same intervention, but with different participant populations. So you want to be able to do things exactly like this. So my question is related to, so do you have a sense of what is the cost in terms of lost precision from doing this sort of meta combination of functions versus doing a combined, what you call a mega GAM? In the second example you gave, it looked like there was some pretty substantial additional uncertainty.
Yes.
So I'm just curious about why that might be.
Yeah, that's a very, very good question. And I think, so this algorithm is a bit heuristic. And I think the reason why the precision is so much lower with the particularly to the right here is that when you fit it with a meta-analysis, the smoothing is done for the full data. And in this case, if you see the red line, so you know, the smoothing penalizes the squared second derivative. So for the meta-analysis, the sort of the optimal in the maximum likelihood sense, the optimal fit was a straight line. So therefore, there is a much more precision when you do the full analysis on the full data. On the other hand, when we did the meta-analysis, some of the contributing studies would not have a straight line here. Others would. And we don't use that information, like we don't use the smoothing parameters when we combine the fits here. And therefore, I think when you start getting, like, say if just one of the contributing data sets here had a nonlinear effect of to the right here, then the whole overall estimated effect will be nonlinear. And when you have nonlinearities, I think the standard errors typically go up. So one thing I would love to do from a more sort of rigorous, with a more rigorous approach would be to try and do something about combining the smoothing parameters, because we really just combine the predictions at each point without considering the global fit when we do the meta-analysis here. So I think, but to the left, we don't lose much precision because here the overall fits are very similar for the hippocampus, even though they don't always overlap. So I don't have any better sense than that, but I think it comes down to actually using sort of a more structured approach when we do the meta-analysis here. It's not clear to me exactly how to do that, but
all right, there's a question from Matt in the chat.
Yes, I can read it. So do you have any plans to try this out for a systematic review, but the groups providing data might not know each other so well? Yeah, we don't really have any plans, but what we wrote in the paper in NeuroImage is that it could be a good idea if people use non-parametric models to actually post, like to share their parameters and their basis functions, so that you could later on, maybe 10 years from now, people could actually do a meta-analysis of these models. So it could be cool. So if people have any ideas, so I think the background for this is that we had this EU project where we weren't allowed to share data, and the whole purpose of the EU project was to get a lot of power by combining brain imaging cohorts from all of Europe. So we developed this package, looked just scratched the surface of the statistical properties of these things, and then we suddenly were allowed to share data. So we we went into what I called mega-analysis here. But if anyone else is constrained with not being able to share data, I would love to chat about it and see what we can do, and I would be very happy to contribute on that.
Well, that left figure there is really like selling this, right? Because you essentially get the same result. So it's very, very convincing in this case that this is working. I have actually sort of a question, if I may, related to this. So sort of conceptually, I mean, well, first of all, this shows that it can work, but let's take a sort of extreme scenario. Let's say you have a bunch of studies for low age, and they're all like this. And then you have a different set of studies with high age, and there's no overlap in terms of the age range, and they are up here. Now you throw them, you get these predictions, and what's going to happen is, right, it's going to be like this, right?
Exactly.
And you find no heterogeneity because they're all really homogeneous over here, they're all very homogeneous over there, and there's no overlap to detect actually any heterogeneity.
Yeah.
Do you see my point here?
Yeah,
isn't that like a concern a little bit with this? I mean, this is of course a bit of a made up example, but there is sort of well, I don't want to call it like like a flaw here, right? But what do you feel about this, or what do you think about this?
Yeah, I mean, I totally agree, and this is not. This was just an attempt at solving one particular problem, and it seemed to work for this particular problem. However, it's not. These things are not rigorously like defined or anything, and you know, to be honest, like I'm a statistician and I don't like to, present things that are heuristics, but these are heuristics that seem to work for this particular case. But that definitely needs more development. As I said, maybe combining smoothing parameters or other sort of information about the curves. And also, yes, as you say, there has to be overlap, at least in parts of the samples here. So there are lots of limitations to this.
So couldn't you, so I assume what you're doing right now is you when you're combining these predictions, if a study doesn't contribute any data for a particular age range, it doesn't contribute to the prediction, right? Like there's no data in this age range for the study. So I assume what you're doing right now.
Yeah, but so what I actually do is like, I just, imagine calling the predict function in R on a grid of 1,000 ages between 20 and 90.
So you are extrapolating.
And then you just weigh it by the standard error of the fit.
But are you when you're doing these predictions for all of the different GAMs, are you also like extrapolating beyond the range of the data that a study has?
That's an option in the package, but by default we don't. So I think my thinking is that you have infinite standard errors outside of the range of the data. It might not, but for our case, there were, if we go a little bit back here, we had overlap, or we had most of the samples covered most of the whole age. So we decided that we don't extrapolate, we only interpolate.
But extrapolation, I'm not sure exactly how this works with GAMs, but I assume that the standard errors will get wide once you go beyond the range of the data. But I think you could predict even for values. Well, that of course definitely possible in regular regression. I don't know about GAMs because you have these knots and so on, so that may not work. But that could be a solution to at least detect or deal with this problem where there is no overlap, because while yes, you get wide prediction errors when you are extrapolating, but at least there's some indication that there is a discrepancy here between.
That's a very good point.
Yeah. But I don't want to, there's another question here maybe in the chat that we should get to, because well, I don't want to monopolize this.
Yes. Do you want to, there are several questions here, but
so the next one, I think, is when the dependent variable is non-parametric and the predictions are non-linear, what will be the recommended approach?
The dependent variable is non-parametric. That's the Y, right? Can you predict non-linear? So I could just say that non-parametric is that's the function. So that's when we use sort of combined basis functions rather than using the data as you do in, or multiply regression coefficients with the data. So I'm not sure I understand that question. But then James asks, would it have been feasible for the central group to specify the knots so that they were consistent across groups? I think that would work perfectly if you have similar, like if most groups cover the full range. So if you use, for example, cubic regression splines, if you have, say, the central group was this LCBC, for example, and they define the knots as 10 knots along this age range, they would be ranked deficient in this Whitehall 2 study. So what they would have to do then would be to sort of use only those knots that were within their range. So that could have worked. It's not entirely, and maybe that could have worked and just removed. So just like made the matrices positive definite, right?
Yeah, the intuition behind this is that just the idea that even though the set of knots would not be optimal for any given sample, right? They'd be sort of undersmoothed or they'd be too noisy. Choosing a common set of knots would make it easier to combine the parameterization of the spines across data sets, and then it might be closer to optimal for the full pooled distribution of age.
Yeah,
you understand the individual data sets.
What we would have to make sure then is that we drop, but that's not that hard. So if you use knots and we just drop the knots that are outside the range, so for each study, when they want to fit the model, they would have to sort of remove from the predictor matrix or the data matrix, they would have to remove the knots that are not in the range because they're constant, and then use the knots that are in the range and return the estimates for those. But then I wonder, yes, so then it means that for the knots that are outside of the data range, we would have to set the variance to infinity or something, right? Not combine, not use it. Yeah, I think that sounds like a very good idea, and I haven't seen it published. I searched quite a lot for these things when I made this, and I think that could be probably sounds like it should give a better global fit, or meta-analytic fit.
So we'll be looking forward to your next presentation on Metagam 2.
Yes.
All right. So I think this brings us to the end, also sort of right on time.